So here we're looking at the part 2 of our video series with probability. And this is an example where probability models where we deal with geometric probability. The geometric piece comes into play because we're looking at, in this case, area of a circle and the area of a square. So for instance, on Harrison's dartboard, the side of the square is 20 inches. So then we know we have a square and all the sides are 20. So when we're thinking about total area, this would be a 20 by 20. So it would be 400 square inches. So without the circular dartboard, the square would be 400 square inches. So if a player were to throw a dart and it land inside the small circle, so we're talking about right inside here, we want it to land in there. Now, first let's notice some things. The radius of the large circle is 10. Okay, so when you're thinking about from the large circle, that would be 10, that would be 10, which creates your 20 from the board. Okay, so the large circle has a radius. So the radius of the large is 10 inches. The radius of this medium size, or the middle one, we notice right here is 5. So that middle circle is 5 inches, and the radius of this small circle is 2.5 inches, which would be that section right there. All right, so if you're going to hit in the center of the smaller section, you're going to get more points. So we're asking, what's the probability that it would land inside here? Well, we just do some computation. So we would want to know the area of the circle, and that is pi times the radius squared. That's your formula. So we need to take the radius of the smaller circle, which is 2.5. So we're going to take, and we're going to approximate pi to be 3 1400ths, approximation. So 3 1400ths multiplied by 2.5 squared. So when you take 2.5 and multiply it by 2.5, you're going to get 6 1/4, and you're going to multiply that by 3 1400ths. Now that just gives you the area of that, what I've already circled and colored in, which would be in green. So the probability of it landing in there would be 3 1400ths times 6 1/4 would be 19 625 thousandths out of 400. So the probability of that happening is about a 5% chance, approximately. When you take 19 625 thousandths divided by 400, because that's your total area, is the 400. 19 625 thousandths is your area of the smaller circle. And take that answer, divide it by 400, and you'll get, you'll get something like this, which you can approximate that to be 4 9/10%, or approximately 5%. Makes sense? It's a small area to land that dart in the circle. So now let's look at, what about the middle circle? So we're saying, what about the middle circle? We want to earn 25 points with this. So in order to do that, we need to know, well, that radius is going to be 5. So that area is going to be 3 1400ths multiplied by 5 squared. Well, 5 squared is 25, and we multiply that by 3 14/100ths, we're going to get 78.5 square inches. So just take 78.5 square inches and divide it by 400, which we already know that's bigger than 19. 19.5, which is what we saw on this 19 and 625 thousandths. We know that 78.5 divided by 400, that's going to be approximately 19 6/10%. So you've gone from a 5% chance to almost a 20% chance of landing it into the middle circle. So now you're looking at, well, what's the probability of landing it inside that section? Would be 19 6/10 chance, and that would be representing the entire piece right there, okay? Because that region, that 5 inches represents from the middle outward. So if you know that it's 78.5, so if we take 78.5 and we subtract it from the 19 625 thousandths, we're going to get about 58 875 thousandths. When we divide that by 400, we're going to get about 14 7/10% chance of landing in the region that we're talking about right here. That middle circle. All right, so let's look at another one. So what about landing inside the larger circle? So now we're talking about what happens if we landed inside this region here, okay? Well, what we could do is figure out if we figure out the area of the entire circle, which would be the radius of 10, and we subtracted away the entire middle circle, then that would tell us what would be left over in this purple region. All right, so we would take the area of the large circle, which has a radius of 10, square that, multiply it by 3 14/100ths. So 3 14/100ths, and we're multiplying that by 100. So that would be 3 14/100ths divided by 400. And so that would be a 78.5% chance. But if we want to land it in that, we're going to have to subtract out the area that consists of the radius of 5 centimeters, the 5 inches. So we're going to take the 5 inches squared times 3 14/100ths. So remember, that's 25 times 3 14/100ths. And that's just the percentage there. So we need to take 25 times 3 14/100ths. That's going to give us 78.5 out of 400. So the 314 take away 78.5, all of that would equal 235.5 divided by 400. So the probability of it landing in that larger circle would be almost 60% chance. All right, in this next section, we're going to look at tree diagrams. We've got two friends that meet at a grocery store, and they remark that a neighboring family just welcomed their second child. Turned out that both children in the family are girls, and they're not twins. And one of the friends is curious about the chances of having two girls in the family's first two births. So if you're thinking about how that may look in a tree diagram, what you're going to see is, well, with their first birth, you're going to have a boy or a girl. After that, with your second birth, you're going to have boy or a girl. If you had a boy, first birth, second birth, you could have a boy or a girl. If your first birth had a girl, you could have boy or a girl. Okay, so that's what your tree diagram would look like. And we would notice what are the results. Okay, so if we've got boy, girl, boy, girl, boy, girl, what would first birth, second birth? What we would notice is we've got four outcomes. We would have boy, boy, we would have boy, girl, we would have girl, boy, we would have girl, girl when we're looking at that. Okay, so looking at the probabilities of each stage, and we looked at the four possible births. So on this next one, what's the probability of having two girls in the situation? Well, the probability of having girl, girl would be 1/4. Probability of having boy, boy would be 1/4. So if we said, what's the probability of family having two girls in the situation? We said would be 1/4. Is that greater than or less than the probability of having exactly one girl in the two births? Well, exactly one girl in the two births would be here. It's a 50-50 chance. And here you see that you have 2 out of 4, so it's also a 50-50 chance. So to answer that second question, is it greater than or less than the probability of having one girl? Well, the probability of having girl, girl is going to be less than the probability of having exactly we would say exactly one girl. That would be 2 out of 4 or 1/2. If we look at another example, so imagine we've got a family of 3. This is a different example, so just disregard that copy and paste there. Imagine that a family of 3, you've got Alice, Bill, and Chester, play bingo at home every night. Each night, the chance of one of the 3 players will win is 1/3. So what you have on the first night of winning is Alice could win, or Bill or Chester could win. So using A for Alice, B for Bill, C for Chester, and the tree diagram show that we're going to have 9 possible outcomes on 2 consecutive nights. So like I said, the first night, Alice, Bill, Chester. Now, what could happen on the second night? Well, Alice, Bill, if Alice won on the first night, Alice could win on the second night. Bill could win on the second night, and Chester could win on the second night if Alice won on the first. Same for Bill. You got Alice, Bill, and Chester. And then if Chester won on the first night, you have Alice, Bill, or Chester. So those are your options for, so you could have Alice winning both of them, Bill winning both of them, Chester winning both of them. And then you would see that you have 9 possible outcomes. And so is the probability that Bill wins both nights the same as the probability that Alice wins the first night and Chester wins the second night? Well, Alice wins the first night, Chester wins the second night is 1 out of 9. And then is the probability that Bill wins both nights the same as if Alice wins the first night and Chester wins the first night? Well, then here's when Bill wins both nights. So both of those are 1 out of 9. So those would be the same. And then probability, like I said, of each one winning is 1/3. Probability of Bill winning both nights is 1/9. The probability of Alice winning and then Chester winning would be 1/9. And here's one more example with compound probability. And here's with using tree diagrams. And so here we've got a Washington, D.C. lottery website, cherry blossom doubler instant scratch game. So the chance of winning a prize on a given ticket is about 17%. So to win is a 17% chance. To lose is an 83% chance. So draw a tree diagram to show the 4 possible outcomes of playing over these 2 days. So this person stops at a convenience store and works from home on Monday. So to buy a scratch ticket to play the game. So on Monday, you have a chance of winning and a chance of losing. On Tuesday, if you won on Monday, you could win on Tuesday, or you could lose. So you could win or you could lose. You could lose on Monday, win on Tuesday. You could lose on Monday and lose again on Tuesday. So with those results, you could have a win, win, a win, loss, a loss and a win, and a loss and a loss. So think about the probabilities. Well, if you win, win, that's going to be a 17% times a 17%. Or a 17% times an 83%. Or an 83% times a 17%. Or you could lose both of them, which would be an 83% times an 83%. So the win-win is multiplying those probabilities together. So, and that's this first one right here that I want to calculate. So that's 17 hundredths times 17 hundredths, which is this number here, which is about a 2 8/10% chance of winning both days. Very small. The win-loss or the lose-win are both going to have the same probabilities. That's 17% times 83%. So you've got about a 14% chance that you're going to win on one of the days and lose on one of the days. And then the probability that you're going to lose both days is 83% times 83%, which is a high probability of losing, which is about a 69% chance. So there you're using your tree diagrams and knowing what your results would be for winning and losing, you can use your probabilities and multiply those probabilities. Let's look at another example with a tree diagram. Donna's in the front seat, and Alan, Benjamin, and Carly are in the back seat in alphabetical order. They've arrived at the beach, decided to get a bite to eat the burger bar. There are 3 burger choices. You've got veggie, turkey, and beef. There are also 3 choices of cheese, American, Swiss, and cheddar. What are the different types of burgers that they can make? Well, you've got veggie, turkey, and beef. And based on those, you have 3 choices. And those choices would be American, Swiss, or cheddar. So the different types of burgers can be made are from this tree diagram. So suppose the customers also want to choose from white, wheat, or pretzel buns. How does this change the tree diagram? Well, remember, you've got veggie, turkey, and beef. And you've got American, Swiss, and cheddar. But if you're also going to bring in 3 different types of buns, now look at how that changes. So each choice is going to have the white, the wheat, and the pretzel. So you actually have 3 choices of let's see, what did I say there? You got your 3 choices of burgers, 3 choices of cheese, and 3 choices of buns. So you're going to have 27 possible outcomes to choose from, which is very similar to what you have in the choices when you go to Subway. You already kind of know what you want, but you've got different types of bread, different types of meat, you've got different types of toppings. So this is your counting principle, which allows you to multiply to figure out what those different outcomes would be. So tree diagrams can be used to organize the outcomes to determine the sample spaces. All right, let's look at another example. This is compound events. So when you're thinking about compound events, all right, you've got the yogurt machine is going to randomly give chocolate, vanilla, and cake batter. They also get 1 free topping from 4 choices, and here's your 4 choices. What's the probability that someone would get cake batter flavor and rainbow sprinkles? So the probability of getting cake batter and rainbow sprinkles. Cake batter is going to be 1 out of 3. The sprinkles is 1 out of 4. So what you're going to have is multiply these probabilities to get 1/12 chance. Now, you could use a tree diagram to check on this. You'd have chocolate, vanilla, and cake batter. And then you're just going to have 4 options. And so of these 4, 8, 12 possibilities, you're looking for cake batter and sprinkles. There's only going to be 1 of those. So that outcome is 1/12. Well, you can also get that shorthand is by figuring out the probability of your cake batter, which is 1 out of 3. The probability of getting sprinkles is 1 out of 4. You're using the counting principle of 3 times 4 to give you the total sample space. and then there's only one of those items that you want, so it would be 1/3 times 1/4, which would be 1/12. Here, Benjamin's ordering pizza. He has 3 sizes to choose from, so small, medium, large, and he's got 7 toppings to choose from. And then pepperoni is one of those 7. So if he randomly chooses a size and a topping, what's the probability that he'll end up with a large and pepperoni? So you're really kind of looking at this area here. What's the probability of getting a large? Be 1/3. What's the probability of getting one of those toppings and it being a pepperoni? 1 out of 7. Randomly choosing a type would be 1 out of 21. And that would be notated as what's the probability of getting a large and then pepperoni. Donna has 4 shirts and 5 skirts to choose from. 2 shirts are her favorites and 3 of her skirts are her favorites. If she randomly picks out a shirt and a skirt without looking, what's the probability that these items are her favorite? Well, of the 4 shirts, and then she's got 5 skirts to choose from. We know that 2 of the 4, we say that maybe these 2. So 2 of the 4 are her favorite shirts. And then her skirts, she has 3 of the skirts are her favorite. But she has 5, but we'll say that 3 of them. So we would say 3 of the 5 are her favorites. So this would be 6 out of 20, or 3/10, or a 30% chance that she would randomly pick out a shirt and a skirt without looking, and that they would be her favorites. So you're thinking favorites of shirts would be 2 out of 4. Favorite of her skirts is 3 out of 5. Multiply those probabilities. You get 2 times 3 is 6. 4 times 5 is 20. You get 6/20. Simplify that to 3/10. And then finally, a box containing different colored marbles that are all the same size. The table below shows the colors and the amounts. Now, if we're looking at the possibility of Alan selecting a marble from the box and then tosses a fair coin, what's the probability that Alan will select a red marble and the coin will be heads up? Well, these are independent events, but the compoundness here is the choosing the marble and flipping a coin. So what you're looking for is the probability that you would get a red marble and the coin would be heads up. So what's the probability of getting a red? Well, it would be 4 out of, well, we need to know what the total would be. So you've got 8 and 12, you've got 20. 20 total marbles. And the probability of it being red is 4. So 4/20, and heads would be 1/2. So this would be multiplying, you would get 4/40, or a 1/10 chance. Now let's look at just kind of something similar to that marble piece. If you had 20 marbles, and what did we have? 4 red, 8 blue, and 3 green and 5 pink. Okay. You can also look at how, what if you were choosing a marble but you didn't replace it back into a bag, for instance? What's the probability of choosing a red and then a blue? But we're going to say we replace the marble. So what's the probability of choosing a red marble? Well, that will be 4 out of 20. And then what's the probability of getting a blue marble? Well, that would be 8 out of 20. That's if you replaced it. You chose out of the bag, probability of getting a red is 4 out of 20. Put the marble back in, what's the probability of then choosing the blue one? It would be 8 out of 20. Well, 8 out of 20, both are divisible by 4. So this would be 2/5. This would be 1/5. So 2/25 would be the probability if you did replacement. All right, well then let's look at what's the probability if you didn't replace. So what's the probability of getting a red marble? Well, that's 4 out of 20. And then if you didn't replace it, well, now you don't have 20 marbles, now you have 19. And then what's the probability of choosing a blue marble? That would be 8. So you see how your denominators change now? It went from 20 to 19. You would have to make that change in denominators if you're looking and you did not replace your amount. So look at one more. What's the probability of choosing a red and then a red if you did not replace? Well, we know there was 20, and we know that there was 4 red. So 4 out of 20, but if I didn't replace it, and I've already chosen a red, and now it's 3 out of 19. So again, back to here. What's the probability of choosing a red, not replacing the marble back in the bag, and then choosing another red? Well, the first one is 4 out of 20, which would be 1/5. If I don't replace it, I leave it out of the bag. Now I've got 19. I don't have 4 marbles anymore, I have 3. So if you did so 5 times 19 is 95. So 3 out of 95, which is about a 3% chance if you don't replace it and you choose it again. So you've already, you've already taken out your total number from 4 red marbles to now 3, and your total denominator changed from 20 to 19. So that's just to be careful if you have a situation like that and you want compound probability, but whether you're replacing or not replacing, it does change your total, which changes your denominator. So that's the end of the second video, part 2, dealing with probability.